ලක් විතරයි. ඒකෙන් තමයි ඒක නවත්තලා තියෙන්නේ.
Sir, ආවා sir
හරි
ආවා.
මේක පොඩ්ඩක්
Good morning.
hello
Good morning.
Hello.
Good morning, sir.
good morning sir
කොහොමද අද? Good morning. කොහරි පුතා මේ ටීවී එකක් හරි මොන හරි ඔන් කරලා තියෙනවා. දැන් ඕෆ් වුණානේ. This topic here, the flow systems and non-flow systems. I hope you can see it. Flow systems and non-flow systems. So we have to understand what flow means, what non-flow means, what system means. Okay, that's why. So always we have to go a little bit beyond the words. So to understand this, left side I put one example. This is a water pump. Okay, water pump. So I think we all have a little understanding at least about water pumps. So in the water pumps, you know, there is an inlet. Also there is an outlet. Means there is a flow in and there is flow out. Yeah, we know this, but knowing is one thing. Once we mention, we know it, but recognizing this, අඳුරගන්න එක දැනගන්න එකයි අඳුරගන්න එකයි තියෙන පුතා ලොකු වෙනසක්. Know and recognizing. යාළුවෙක් කියපුවම අපි දැනගන්නත් පුළුවන් අඳුරගන්නත්. අන්න ඒකයි. There is a difference, so we have to recognize there is flow in, flow out. Okay, and here, so what's taken place is within the impeller and casing here, means inside this pump. Something is happening. Okay, something is happening. As a result, there is a flow out and also there is a flow in simultaneously in and out there as a result of some function within the casing inside. That's why this right side, inside we call the pump system. The phenomena is taken place inside the pump. This pumping phenomena is taken place within the pump. So that's why we can say when it comes to system here, of course, thermofluid flow system. So I just put a block here with dashed lines. Okay. Inside I put pump and I mentioned the word system. So outside the system is the surrounding. You can see the word surrounding. And separation of surrounding and system. We recognize through this system boundary. That's why I put this dash line. So pump has flow in, water flow in here. Pump has water flow out. Also there is a motor, electric motor here. Per motor again, yeah, electric motor is here. So it provides some work to the system. Okay, it provides some works to the system. And also there can be little heat interaction as well. If you really measure the temperatures accurately, even in and out temperatures, there could be subtle differences, even in pumps. So anyway, if there is a temperature difference, it's surrounding. So there is a heat interaction. Somehow there is a heat interaction. So I just put this heat in or heat out, but I put as heat in. So if it is heat out, this heating can be negative. Example, negative 10 watt means in, minus 10 watt means out, plus 10 watt. In 1 kilowatt means if you take this work out, that is minus 1 kilowatt. So it's a sign convention towards the system or out from the system. Okay, but generally when it comes to work and heat, always we put the arrow considering this is towards the system. Okay, towards the system. So here right side you can see on top I mentioned flow, work and energy model. So this is the flow, work and energy model. Okay, so that is what it is. Okay, and you have in and out. So that's why when we have in, flow in means mass flow in, here it's water. And there is water flow out. There's a mass. So that's why we call this flow system, or we can call this open system. Okay, flow system or open system. So I'm going to the second one because understanding is very important. Yeah, because if we don't understand in very detail in this way, we have to remember the equations. Remembering equations means you have not recognized it. That's the issue. So if I go to the other slide, yeah, of course, the same thing here. So this is a flow system. So I strike out non-flow. Okay. So this is not a closed system. This is a flow or open system. So I highlight work, flow and energy model is right side. I put surrounding in a bit greener color. Boundaries there with the black dash line. And the system is shown here in white. It's the same thing, but for the ease of recognition. Flow in there, flow out there, work in, and there should be some heat in. If no heat in, we consider heating is zero, but for the system we take there is a heat in. Can be zero. Okay, anything can be zero anytime. Okay. So this is the situation. And I introduce the word steady flow here because for this case, generally flow can be considered as steady as long as the work done is steady and the inlet, the head, no change, outlet head, no change. So there can be some steady flow. But later I will explain what steady really means. Okay. What steady really means later I will explain to you. Okay, so At the moment, you consider flow is steady. Whatever in steadily goes out. Okay, so the in can be same as out. So we will go for one more example. Air compressors. I think you know better than me about this. Again, like the water pump in and out, here I just put this could be the in through this filter of whatever. Flow in. Here the air flow in. And then this is the compressor, two-stage compression. You can see the one wider one and another, the narrow diameter one. So this is a two-stage and the connections are there in between. So this is two-stage somehow. Two-stage together if we consider as a system. Out is here going straight away to the high pressure air or compressed air storage tank. So again, you can see in and out. Okay. And in and out. And I put again the same way, green color surrounding and white color system, and separating surrounding and system, the system boundary in this way as a box with dashed lines. Here also, I didn't change the model, it's the same. In and out of the flow, here should be airflow. Of course, work in, you can see a motor here, electric motor, through the belt drive system. Somehow there is a work in, and heat interaction is obvious. You can see the fins here. Fins here, some lubrication, cooling systems are there. Because some internal heat is generated, so this should be dissipated. Even in the high end, the two-stage compressors, you can see the connection also, you can see there are fins to cool down. Let's say it is something like intercooling or whatever. So you can see there is a system heat interaction. Heat interaction, so here it's with the surrounding. So heat is released, but here we put heat in. So it can be negative when it is really out. Okay, I hope you can understand this. Without the example, if we discuss the right side model, no much sense really. This is a compressor, refrigerant compressor. Again, right side only changes the refrigerant compression system. So this is, you can see in and out again. In is the suction, out is the discharge. Okay, and electric motor is here with the windings. You can see the rotor here. Okay, and other pipe is the service pipe. It has to be. And this is inverter type. You can see the electronics here at the left side. Whatever. You can see there is an in and out. That is common. That's why again right side there is an in and out. Okay. So surrounding is there, of course. Once this is in operation, this compressor is bit, not to say bit, is quite hot on top because of the motor heat. So even the compressor itself, there is heat interaction. Even sometimes there are fans to cool the compressors. Sometimes the static cooling, no fan, but the cooling is taken place. And the compressor is black because the heat can be radiated. We call these compressors black compressors. Black compressors. So that's how we name this. Again, the modeling is the same, in and out. So again, this open system, flow system. Some examples. Here also in the proper operation, we expect some steady flows. So steady is still a word for us. We will see what steady means in a much better way, of course, steady flow. So what's steady for the system? That is important. What's steady for the system? And this flow we call working fluid. What is flowing is working fluid. So here some refrigerants flow through the compressor. So refrigerant is the working fluid. In the previous example, air is the working fluid. Very first one, water pump, water is the working fluid. Okay, means water performs something. Yeah, that's what even here refrigerant is ready to do something. Yeah? So this steam turbine. I got this picture from internet. So you can see steam entry here, steam out, turbine blades are there. So then this rod, the turbine outlet goes to the generator. Generator is coupled. Okay. Then generator is being turned here to produce electricity. So when the electric load is there, the generator load is on the turbine. So turbine, there is a work done by the turbine, work out. And also, these are huge. Even there can be, in our Norochole, Lakvijay, we have 300 megawatt, I think 3 steam generators. The steam power plant generators. Yeah, steam turbines, we call it, not to say generators. We have huge 3 megawatt steam turbines, but there are, so this will be 3 times 4 later. This is 1200 megawatt generation from Norochol using 4 turbines. But there can be even single turbine generating 1200 megawatt. Yeah, so those are massive machines, and of course you can see the heat is, of course, dissipated from the casings. So these are very high tech. Also heavy engineering products. If you look into, let's see, if you look into some photos of turbines, one chat is here. It's okay. Let's browse some steam turbines. You can see the massive ones. So it's normally very reliable, quite reliable. There should not be failures. So these are actually, that's why now you can understand how tacit knowledge is important. So these turbine makers, even biomass power plants, there are steam turbines. So turbine makers, they are doing this for generations and generation, not just one time. And most of the innovations here, we would say innovations and developments, not based on books, but of course based on some innovations, analysis, experiments, trial and errors, and finally all comes as a knowledge. Those are not in the books, even to address the reliabilities, because once installed, we should run with no issues for 10, 20 years by right. Unless there are times for the preventive maintenance, these should run. Even this old one. This looks old one, the Mitsui. Yeah. Turbines. Anyway, quite heavy, mega engineering pieces. You can see how they are working here. So no matter how big, only 2-3% are getting involved. So high tech, very skillful, heavy engineering jobs. Yeah. Even installation is tough. So turbines, massive ones. See, these are being turned by steam. See how powerful steam. Steam is more powerful than turbine. You know? Yeah. Anyway, steam power is steam power through the turbine delivers some great work. Let's see, 1,200 megawatts. Sometimes that power is from the steam. See how powerful the steam. Yeah, can turn huge generators by driving this kind of massive turbines. And those are really wonderful, you know. You have to feel these things. Yeah. So you have to feel not only this, the steam. Yes. How wonderful the steam. Yeah.
So excuse me.
Yeah, Buddha.
So what are the material that using steam turbines?
Buddha, hard to say that one. Those should be some special alloys. Yeah, mainly should be metal, ferrous based, but those are special alloys, and those are really maybe trade secrets. Yeah. You can browse the type of metals and all, but to have no rust, that is one thing, and also there shouldn't be much thermal expansions. Yeah, and also for high speeds, also to have this flawless, no fatigue failures, to assure no fatigue failures and all. I think those should be some special type material. Somehow they form into special type of material, if I'm not mistaken. Special steels. Special means not mild steel, but treated, surface treated, also maybe alloy. So, anyway, thank you for the question, Buddha. So this is the situation. Even here you can see sometimes the 1,200 megawatt. Yeah, let's see, 200 megawatt steam turbines. The Russians always do the big huge ones. Yeah, see. Yeah, this is assembling 1,200 megawatt steam turbine. You can see the picture here, the right one. The Russians one also, they have different technologies. Maybe. So anyway, we also can think of producing small ones. Yeah, because we should think that not the best steam turbine is developed so far. Maybe you are the one developing. We have to think in that way. Okay. We have to think in that way. So even these bigger ones, not one shot they develop this step by step. From the smaller capacities one to medium ones, and through the experience they build this. That's how they do this. So you also can try. Here the blade technologies. all the things. It's very interesting. Safety also very important. High pressure machines. It's quite nice. General Electric also doing this. General Electric. Skoda should be in Yugoslavia. Siemens, Germans are doing this. So you can see that those technologically advanced countries, they produce steam turbines. Those are massive ones. Even the Noroccioli, when you imagine, it can power so much of motors in appliances, industries and all. They are massive ones. So, but the efficiency, you can see efficiency of steam turbines is little higher than the other gas turbines maybe, but efficiency is around 50%, maybe the best ones. That's why. So these are the issues really. In the thermal systems, it is not possible to use 100% of available thermal energy to convert into work. Let's say 100% impossible, we know that. But at least certain percentage. But as I know, it's about 50% maybe. The best ones around 50% maybe. Turbines. So that's the situation. Yeah. Later we will look into those. But we will do the examples, steam turbine examples. So back to the slides. So here, no matter how big or small, so this is the basic flow, work and energy model. So this is what we are learning. But when it comes to the analyzing of the real ones, the latest approach is they call finite elements, finite element analysis. Even for heat exchangers, when we analyze thermodynamically the heat transfer and all, we go for pipe by pipe in the heat exchanger. Even in single pipe, we go for element by element. So finite elements. So that's how we analyze the heat exchangers even now. So turbines also by right should be finite elements, because they are studying one particular element. Sometimes the elements of elements. Example, if blade is an element, turbine blade, then this turbine blade also consider as many elements. Yeah, that's how we do the analysis. So it's very interesting, and when you need to use the finite elements, you should know computer programming, because without computer programming, it is impossible to analyze thermal systems. If cannot analyze thermal systems, you cannot design thermal systems, but you can construct. You can do basic designs, but you cannot optimize. And that's why. So computer knowledge, the coding knowledge, programming knowledge is extremely important if we need to further into analysis. Even yesterday when we talk about this dryer for the Hadunkuva incense sticks, so if we really looking into the analysis, finally it will be finite elements, or can be finite volumes. So finite elements and finite volume analysis, extremely important. Yeah. That's why slowly but surely you have to learn programming. So programming C++ is is not just for passing the exam, but it has an enormous value. So it has an enormous value that you can make use of. But those who are teaching this programmings, they may have no idea about the applications. But we know how serious the applications. So better learn the programming, the coding very well. Even don't wait for the lecturers to teach programming. You can learn by. There are a lot of self learning facilities in the net. So also there are some working groups there. So you can really go to those websites and you can learn. Yeah. So again, here introduce the steady flow. It's the same system, in, out, work in and heat in. So the very raw model, but even for element level, you are doing this. Even in finite elements, let's say if you take a heat exchanger, a small piece of heat exchanger, a small element, still this is the case. You have the small element as the system. There is flow in, there is flow out. There can be work in and out, work in, network in, and there can be net heat exchange. That's why even for finite elements, this is the case. Yeah, let me example. Let me insert one slide here. Okay. I take heat exchanger tube. I just take heat exchanger tube. Let's say it's a pipe. Let's say this is a pipe. So I have to write it as a pipe because otherwise pipe. And let's say through the pipe passing bit hot fluid, can be steam or something. Yeah? Can be steam. So you know that I need to pipe it like this. So you have flow in and there is flow out. Okay. Through the pipe. Okay. So flow in I will put as this. And the flow out is something like this. Okay. So there can be other flow in and out as well. Tube side is that for the outside the tube also there can be flow in and out. Okay, for flow in and out. Possible. Okay. So now let's see the situation. Yeah. So there is a heat interaction for sure. There is a huge heat interaction. There is a huge heat interaction. I use a different color because otherwise you cannot see. There is a heat interaction. Okay. Heat. So I will say just heat. Okay. transfer. So this one is maybe from tube to the outside, but I just put towards the tube. See the heat effect. And flow in, flow out. Okay. There is flow in, flow out, and again flow in, flow out. Okay. You can see. Somehow if you think of through the pipe, okay, if you think of the pipe here, you can see in, out, same like here. Surrounding is the other part. Okay, heat interaction is at the surrounding, with the surrounding. So you have heat, flow in, flow out, and here work may not be, unless there is a friction. If there is a friction and pressure drop, you can consider some. Okay, but anyway, that is again for energy balance, so you have no work, zero work out. So you can model. And now for the finite element, let's say if you are going to take a small piece of pipe, this piece, okay, this piece of pipe, it's a small piece of pipe. Still you can see there can be flow components passing through this. The big flow, there is a corresponding flow component for this. And flow interactions externally can be like this, and then there can be flow in for this. Okay, so yes, flow in. Even there can be flow out. Flow in and out. See. So this is the system. This is a finite element or finite element, let's say. Exactly like this. Same like the pipe. You can see, yeah? Yeah. And of course, I forgot to put the heat interaction here. There is a heat interaction as well. Very good. So no matter it's a big pipe, it's a small pipe, okay? You can notice that. See? In, out, yeah, of course. Tube outside is for the heat interaction. Somehow heat interact. So you can see it's an open system. So no matter big or small, so this model works. Okay, this model works. So that's why very important to understand these models. Yeah, very good. So flow, work, and energy models. So this new addition to the slide. in addition to the slide. So that's why nowadays, when you analyze heat exchangers, you are going there. There can be a bundle of pipes. So you are analyzing each and every pipe. And in each and every pipe, you are taking elements like this. So finally, this can be thousands of elements. This heat exchanger is thousands of elements. Even I did some heat exchanger analysis this way. So no matter it's an element, no matter it's a big pipe, model is this. The model is this. Okay. And here, if you think of another element, let's say closer to here. The first one out is the second one's in. That's why you can see the connections in between as well. Don't worry, but these things you cannot use calculators. Okay, you cannot use calculators, and sure, you have to learn programs. You know, doing programming, it is not maths. Okay, even there are programs, they have no maths background. So programming is an art. There are techniques, okay? There are methods, and you can find your own ways of doing programs. So everyone has the right to learn how to do programming. So here it is very good. So if you can analyze heat exchanger, why not? You can provide really the very good technology contributions if you can analyze this. But even before analyzing, you should be able to understand and recognize the systems without equations. Example, yesterday we talked about dryer, Handunkuru dryer. So we talk a lot, but no equation. That's basic understanding is very important. And if you have a very good understanding, you no need to spend time on analysis like this. You can go with your own judgments and you can solve the problems. Yeah. But if you are a dryer maker, that's the difference. If you are a dryer user, you can go for your judgments. But if you are a dryer maker, we must do the analysis because we are producing dryers for the others. So we should be able to analyze it. If we are heat exchanger makers, we should be able to analyze and manufacture, design, manufacture. That's why. So component making, equipment making, analysis is very important. Yeah, good. So this one we know. So the right-hand side model is quite universal. It's quite universal. Yes. And I have introduced the steady flow word here. The steady flow can be mass flow in equals mass flow out. Okay. And that can be the flow balance. Okay, that can be a flow balance. Balance is a good word to use. Okay, it's a bit technical word, but flow balance is a good word to use. So steady flow means it's a flow balance. It's a balanced flow. Somehow flow should be balanced. Yeah. So then there may not be any impacts or anything. So imagine within the turbine, the fluid there doesn't feel anything. Yeah, here the control volume. The turbine doesn't feel like the same thing comes in and goes out. So look some steadiness here. The energy level remains the same. Mass levels remains the same, mass and energy. So it is something like the steadiness. Anyway, steady flow is mass flow in equals mass flow out. And that can be flow balance. So this steadiness is for the system. System is steady when in and out are the same. Otherwise, if more in than out, system will be pressurized. That is unsteady. And less in, more out means system can have a, that is not possible even. Even if there is a possibility, you can see the negative, something like a vacuum or the phase changes possible. So that is not good. So the steadiness is good to have, and we are studying. So now the steady flow systems we are going to study. Yeah? So even this one, you can see I got this from internet. So again, open system, the flow in, I put the arrows, flow out and heat in and heat out. In because of the burner, loss from the casings here, from the shell. So net heat in is the right side model. I just put heat in. That is considering losses and the heat in, everything I put as heat in. So this is steam turbine system. They are flow in, flow out. And even work in can be 0 here, but okay to put work. And you have the boundary here and the surrounding. Quite interesting. Yeah? Now you have the feeling about this open system or the flow systems. Steady flow. This is one more thing. Let's say example, this turbine. No flow in, no mass flow out. Again, the flow balance is there, nothing in, nothing out. But if a flow system has no flow, then this is not life. Means this is not working. Example, pump, water pump. If no water in, no water out, it is not working. Means it is not live. It is not commissioned yet. Okay, or it's not start yet. Or it is not running. Same for turbine. In, out. If nothing, it is not came into life. So one way is, of course, there should be flows in open systems to bring the system to life. We bring the machine or the equipment to life. There should be flow in and flow out. The flow is really the matter for these things. Huh? This is a separate one. You won't find this in textbooks. Huh? Yeah. So no mass flow in, no mass flow out. So no work, no heat. Yeah. So it is nothing. So system is not live. Yeah. So to work or to perform, we have to have the flows for open systems. So here, of course, this should be live and continuous operations. Okay. This should be live and continuous operation. So there should be mass flow in. Okay. There should be mass flow out. Okay. There should be net heat interactions and work interactions. Same like this. So here, the continuous, live and continuous. Continuous, the better word is steady. So here I put live and steady operation. Okay. So now you have the familiarity of this systems. So mass flow, yeah. Mass flow, the steady mass flow balance means in equals out. So mass flow in equals mass flow out. Energy levels are different, so that is flow balance. In equals in out. So same way we can look into the energy balance. Okay, in this black box, yellow color here, work and energy balance. We need to identify the terms. There should be energy in together with the flow. There should be energy out together with the flow out. And of course, heat interactions Q, I put as Q in. And the work done on the system. System means it's a fluid system. For the thermodynamic system here, work done on the system. W I put as in. And of course, we have to consider timing. Okay? Because heat flow, it takes time. Work done, it may take time. So time can be a matter. So T means time, measured time now. Let's see, this T means, if now time is 10:21, this T can be 10:21. Delta T means starting now, let's say 30 minutes. So then after 30 minutes, the time is 10:31, but the delta T is 30. Something like T and delta T. Right? So these are the parameters. So then the same thing here. Now, yeah, mass flow balance is okay. The yellow color one, mass flow in, mass flow out, M equals out. We are working on now work and energy balance. So we have identified the parameters. Now let's see, for a given time period of delta T. Delta T. For convenience, I put 10 seconds. Never mind. Okay. So this period of time, there can be certain flow of energy in. There can be certain work on the system, that is we call in. There can be heat interaction, I put Q in. Okay. And there can be energy leaving with the flow, energy out, E out. Okay. So these are the things, the interactions. Okay. The interactions. So what happens is, this is the net energy interaction, in minus out. So what happens because of this in minus out of energy? You can see the black box, the bottom line. Net energy and work in minus net energy and work out is the energy rise in the system, delta E system. Delta E system. That's why steady means no system energy rise. That is the important point. No system energy rise means the system doesn't feel something changing. System looks steady. So this is steadiness is for the system. Okay. No system energy rise. So same thing. Now you can see steady operations I mentioned here on top. I think if I do animation, this is better. But now you can see here steady operation, delta E system is 0. Means that no rising of the energy levels within the system. Delta M system, no rising of the mass. Maybe for a given 10 seconds, for a given time of delta T. So you can see again, E in plus W in plus Q minus E out is delta E. For steady flow, this is 0. For mass also, M in minus M out is delta M system. This should be 0. So steady means no energy variation within the system, no mass variation within the system. That's why now you have a better understanding of steady. So better think of the system. Some water is there, some gas is there, of course. Through the system it's flowing, but this is the situation. No energy level rise, no mass level rise. If no energy level rise, energy and work in should be same as energy and work out. No mass level rise, mass in should be mass out. So this is a nice slide. Okay. So then mass balance is, we call it conservation of mass principle. Okay. Conservation of mass principle. Energy balance we call conservation of energy principle. So energy balance, net energy in Q in plus W in plus Q, E in plus W in plus Q minus E out is delta E system. That is the balance. When it is steady, this is zero. Okay. So conservation of mass, conservation of energy. So here, this is conservation of energy, energy balance. Okay. Good. And then let's say, yeah, it's the same thing. So I just highlight here steady system is delta I system 0, delta M system 0. It's a kind of steadiness is this. Yeah. So that's why I highlight that. So then everything here in this slide is the same. Mass in equals mass out is mass balance. Energy in, you know, it's the basic from the basic model. You have the energy in with flow in, energy out with flow out. You have heat in, and also you have W. So in plus W, in plus Q, in minus Q out. For steady system, it is 5%. For steady system, it is. Now, even for 30 minutes, yeah. So delta T, if now time is 9, 30 minutes means 9 to 9:30. Or can be 9:30 to 10. So delta T is the 30 minutes. You understand? If 30 minutes means starting now, it is 10:28. So 10:58 is the after 30 minutes, so delta T is 30 minutes. 10:28 to 10:58 is again delta T. So that is for the time increase. It's for the coming time, not the past. 30 minutes doesn't mean we are going from 9 to 8:30. No, we should go from 9 to 9:30. It is something like that. Time also increase. Other parameters also we consider increase, but if it's an increase, it can be negative. Okay, so that's it. So this is about the delta T, understand. The next one is, let's see, M in minus M out is delta M, that is 0. If this is for given 30 minutes or delta T, this can be per delta T seconds. This is for delta T seconds. Delta T is measured in seconds. So as a rate, you can divide this by the time period. Okay. So when you divide it by time, so it's a per second. So it becomes a rate. So M, rate of M in equals rate of M out. So during 30 minutes, you can have certain mass in and out. So per second, so if you divide it by how many seconds? 30 minutes means 1800 seconds, you will get the rate. Okay, same way. Flow the work also, we can consider rate of energy in, rate of work in, rate of heat in, minus rate of energy out to the flow is zero as a rate, kilojoules per second. Again, you follow the conservation of energy principles. I believe you can understand this. If you have any problem, please let me know. So rate, there is a nice notation for mass flow. We call m dot. This is a notation. M. You have, otherwise you have to write rate of m in. So rate of m, I just use m dot. Rate of m, m dot. Same way. Rate of e, e dot. Rate of w, w dot. Rate of q, q dot. Rate of e out, e dot out. Okay, but that is also quite interesting. Yeah? Rate of e dot is e out. So then this rates divided by the rate of mass. Again, okay, because divided by m dot. So then this is something like rate per kg also. So E dot in, I just use simple small E dot, small W, small Q. Okay, small Q. So that's how you can consider. So here kilojoule per kilogram per second. That is okay. Now you came to understanding this. Okay, understanding this. So understanding this, we call it, yeah. What is E dot and E? Energy contained in the flow. Okay, energy contained in the flow. You have the equation here in the previous slide. All right, check. E dot in. This is the energy contained in the flow in. Okay. E dot in. E dot out. Energy contained in the flow out. Okay. And W dot and Q dot are directly to the system. Okay. So now this E dot in and E dot out. Also, if you think of this, it's the same thing. The big is E dot N. Okay, so energy with the flow. Okay, energy with the flow. So W and Q in are directly to the system through the boundary, directly to the system. But with the flow, this is E dot in, E dot out. And this is the steady flow expression. So above two expressions, we can call it, okay, steady flow energy expressions or equations. Yeah, let's say expression. Because this is the energy in the flow is E in, okay, and energy in the flow is E out. So then when we consider this is the flow is steady, so we can say steady flow energy expression or equation. Okay, steady flow energy expression or equation. This one. Yeah, steady flow expression or equation. Either one is okay. Now you know what steady flow means. Further, so I will take this E in and E out to simple E in and simple E out. So this E in, E out. So here E dot, don't worry, E dot toy. So these are the rates. So steady flow energy expressions equals 0. So here E dot or E, small e dot, is a combination of several types of energies. Let's say what E dot contains. Okay, so what E dot contains. What dot and even small e dot. Okay, what e dot or let's say the energy in the flow in and out contains. Okay, E dot energy in the flows of in and out contain. Okay, energy. So energy in the flows. Energy means energy types. Okay, energy types. We use the word types here. energy types. Okay, you have kinetic energy because there is a velocity flow in and out. Potential energy, mgh, you know, right? Potential energy. This is gravitational potential energy. It is there everywhere. So in any system, this gravitational potential energy should be considered. So potential within bracket, I put gravitational. We have to consider this. In our O levels, we learned this mgh, that is gravitational potential energy because of the gravity effect. The coconut in a tree, let's say the height h, mass of the coconut m, so the potential mgh. So that energy, once the coconut release from the tree, that mgh energy is going to deliver. How? Finally, when it reaches the ground, zero potential energy but very high speed means a very high kinetic energy. So again, energy balance. Potential energy turned fully into kinetic energy. Yeah. So that is gravitational potential energy. Okay, Gurutvakarshana Sambandha Vibhava Shaktiya. For every mass, there is a gravitational potential energy. So that one you have to include it. Every mass, there is a motion. Because of the movement, there is an energy, we call it kinetic energy. Okay, kinetic energy. That's why even when you are moving or when you are running, instantly you cannot stop run. That is not possible because the energy level is there. So you have a certain momentum. So naturally it takes little effort to stop. Immediately you cannot stop. Yeah. Even a vehicle, immediately you cannot stop. Yeah. Train in the move, it takes several minutes and maybe a longer distance to come to its rest while applying brakes. Because of that energy, this keeps moving in. The energy is there, the kinetic energy. So stopping it one shot means removing the kinetic energy in one shot is not possible. So kinetic energy in the fluid, it is natural. If there is a flow, kinetic energy is there. And if there is a mass, potential energy is there, naturally there. And then this has internal energy. Internal energy, U. Okay. And also in this flow, there is another one. We call it flow work. Okay, flow work, but work also. Work also, flow work related energy. Okay, because the flow, you have to push this to the system. Naturally, the flow in cannot be automatic. So you have to push it. No matter it has a velocity, there is a flow work related energy. Okay. And the flow work related energy, we call it energy. Yeah. Okay, but I just looked at the text. So flow work related energy. So let's say this one, I just put this way. And let's say internal energy as U. I just put as U per kilogram flow. Okay. And pressure times the volume per kilogram, specific volume we call. This is flow work related energy. Later I will explain. Gravitational is mg. So m is 1, let's say. Now, mgh, I just put mgh. Okay. Here I put mu. Mu. Here I put mpv. Kinetic energy. You know, half mv squared. mv 2 by 2. mv squared by 2. So these are the components of the energy levels. Okay, different types of energies. I think you can understand this. Kinetic energy is what naturally any moving mass has. Potential gravitational energy is what naturally any mass has. Okay. Other than that, because of the kinetics of the molecules, you have this internal energy U per mass. So if you have mass m, it is mu. And especially there is this PV here. PV term is here. Okay. PV term is here because this PV effect is there when this flow moves into the system. This energy is there. Okay. You can think about this. And then what I do is so your E means, okay, your E. Yeah, E can be, later we will look into the units. So you have mv squared by 2, the kinetic energy component. The total means here, it's okay to combine this together. Addition is the total. Mgh term here. And I change this H into Z from the reference datum because H term we are using for enthalpy. So I change this to Z. Even in previous one, I changed this H to Z. Okay. Plus mu plus mpv. Okay, mpv. Mu. We have learned about the internal energy even in the steam tables. So this is in, it's related to in, out, it's related to out. So this one. So you can rewrite this. You can take m out as its common. V squared by 2. And one more thing. The velocity also, since we use volume, I change velocity to C. Okay, C here. Velocity to C. Okay, so mc squared by 2. So C. Again a standard one. Because we use for volume in thermodynamics. GZ is here, so this is simple math. Use here and PV is here. Okay. Further simplifying this. So the thermodynamics, this is little expressions, but thermodynamics is the other wordings here. Kinetic energy, potential gravitational energy, internal and flow work. So U plus PV we can combine as H, because we have learned enthalpy several weeks ago. Yeah, and these are the reasons really. This enthalpy sometimes combined. Yeah, it's a combined parameter considering U and PV together. So this is very nice. So I will rearrange this. Normally we used to, the more prominent term here is H. The enthalpy is a quite heavy energy value. Enthalpy is a quite heavy type of energy. Then the kinetic energy, then the potential energy. So this is the order I put. Okay. This is the order I put. And I can, this is the order. And I have no space here. No space here. But I have to keep all.
So he said mean height, no?
Height, yes, very good. The height from the data means you can consider maybe from your installed whatever it's a reference data. Yeah, say height. Maybe for the turbine, this may be starting from the mounts. Compression maybe from the mounts. Yeah, depends. Huh? So I'll have to check this again, and I will. Oh, where should I squeeze this? I take this out. The next is I can look into E by M from the same equation. I can look into E by M. E by M. Okay. E by M is this. E by M we call E, small e. Okay. E by M is this. It's per unit mass flow. E by M. H plus C squared plus 2 plus G. It's very nice, sir. And if I take some more space here. E by M is this. And yes, E by M. Also, you can consider this way. Instead of E, you can use see if it's work or not. Dot by m dot mass flow rate. Can you remember? Use the word m dot. Dot is E dot by m dot. Also the same. Okay. E dot by m dot is same as this because it's a rate divided by rate. Okay. This. And one more here. I think this is okay. E dot by m dot. E dot by m dot is this. E by m. Okay. So don't worry about the units at the moment. So we will later, when we look into this complete equation, we will see how we can make use of the units. Now, I take this out at the moment. Don't worry. That's also okay to leave. So now you can substitute this here. Let's say if I substitute here, okay, so E dot in the rate. Yeah, okay. So this is the one. So let's say now how to incorporate this expressions into this steady flow energy expression. Okay. How to incorporate this. Okay. And before that, let's say the units of E. Units of E, let's say this is mgh, so mh, so that is kilojoules. We have to look into the units. This is kilojoule per kilogram. Okay, kilojoule per kilogram. So that is the second one, right? Kilojoule per kilogram. This is kilojoule, the unit. This is kilojoule per kilogram. Okay, E by M is kilojoule per kilogram. Then E dot by M dot. See whether there is a meaning or not. E dot is kilojoule per second. By M dot is kilogram per second. And finally becomes kilojoule per kilogram. Okay, because second, because this is divided by kilogram per second. So we have the divided. So S cancel out. This is kilojoule per kilogram. Okay, kilojoule per kilogram. That is okay. So E dot by M dot is this. Okay. And I will go for another expression. Let's say M dot times E. What is this? Okay, M dot times E. That is M dot times E is this. This is M dot is kilogram per second times E is kilojoule per kilogram. Okay, so kilogram cancel out. This is kilojoule per second equals kilowatt. Okay, even you can take joules per kilogram. Instead of kilowatt, you can consider watts, but in actual cases, all the applications in engineering, it is in kilowatts at least. Yeah. So M dot E is kilowatt. Okay. So I will go for the steady energy combined. This expression in this flow, I take this one. Okay. What's that? E in, okay, E in plus W in plus Q in minus E out equals 0. Okay, let's say. So E in. So based on this, per kg, I will take in small w in small q in E out. Also possible. Okay. Also possible this one also. Let's say, see, I'm going to give some meanings for this. Instead of small w in, okay, anyway, the same thing. Now I take m dot times m dot times multiply by m dot. Okay. So based on this, I will take the terms m dot en, m dot w m dot q in. Okay. And m dot e out. Okay. M dot. Later, let me summarize this. And I will take m dot e in, okay, and m dot e out. Together, you can take m dot e in minus m dot e out. Okay. Plus m dot w in plus m dot q equals 0. Okay, equals 0. So here m dot e in minus m dot e out is m dot e in minus m dot e. Okay, plus m dot. Rearranging this. Yeah. This one, because E in and E out. So we have the term this. Okay. Yeah. E in is, we have the small e. See. This in this out, okay, plus m dot w is, this is big W in, okay. Actually, this is W dot in. W in dot W is W dot in, right? Because m dot W, the unit is, W is kilojoule per kilogram times kilogram per second. This is kilojoule per second, that is kilowatt. Okay, this is W dot in. And this will be Q dot in. Okay, Q dot in. This is a rate, Q dot. Generally, yeah, generally, W dot in and Q dot in is standard is always in, so you can take in out. Okay, you can take out the word in. So finally, you have an expression of this form. In dot and the flow energy in per unit mass minus flow energy out per unit mass. So that is the net flow energy. Okay, net flow energy considering in and out plus W dot plus Q dot. Let me organize this. Let me organize this. So many equations. That is okay. So many equations here. Now we take this. Then we type out in the finally, I will take expressions, of course, based on the understanding of E and E. Final one, let's say, like this. Okay. M dot this plus W plus W dot plus Q dot is 0. Let's see. This is the equation. Okay. The equation. Now we'll go to a model. Okay, I will take this model. So, for this case, okay, for this case, so where you see m dot, m dot is the flow here. For steady flow, okay, flow in is m dot, flow out also m dot, okay, flow out also m dot. Then work in, so this here, the interesting part is here, we are taking all as a rate, flow rate, work also as a rate, okay, heat also as a rate, so all as the rate, okay, and in dot and your energy in per unit mass, okay, per unit mass, energy, okay, and here flow out in dot per unit mass energy out, okay. Interesting, eh? Okay, good. Flow in, flow out. In dot color. We will change to more. Yeah, this is okay. Good. Flow. Okay. Good. Your looks very silent. Eh? See E in here. So this is E. E out. This is E out. So this is the expression. Okay. So if we have started from here, it is easier because the rates, all mass flow rate and per kg energy in, per kg energy out. So that is m dot e in minus, okay, plus w dot plus q dot.
So okay, energy එකක් දාන්නේ මේ rate එකක් විදිහටද?
ඔව් පුතා energy එක කියන්නේ rate එක හැටියට එතකොට all rates. හරිනේ. නැත්නම් time period එකක්. Otherwise it's a time period. delta t වලට මම කිව්වේ තේරුණානේ? all rates. So this way also okay. Let's say for delta t time. Right. So look for delta t. Delta t. Take it from here. So delta t period of delta t period of time then you have no rate. Okay, then you have no rate. Okay, you have no rate. So certain period of time there is an air flow. Okay, there is an air, sorry, fluid flow, whatever. Then we should go into this delta t period of time. So you have accumulated energies. Okay. Let's see, 30 minutes. So within 30 minutes, energy. Within 30 minutes, W. Within 30 minutes, Q. So W no need to put in. We know that is standard. Okay, we'll keep it. So within 30 minutes, E out is W. Sorry, is equal to 0 within 30 minutes. Okay. Okay. Period of time. Delta t. That is delta t. Period of time. Let's say this is at a given period of time. Delta t. See, delta t period of time. So if you divide this by delta t, so you will get the rate. So if you divide this by delta t, you will get the rate divided by delta t. Okay, divided by delta t. Rate. Okay, also equal to 0. And this one, E in by delta t. So that is, we can write this one. M amount in quantity. Some big letters. Okay. So M times En plus, okay, W dot, this will become W dot because W in by delta T. Now let's see. W in by delta T. Okay. And Q in by delta T. Okay. Minus E in. So I need delta T here also. So here, so one term is M dot, sorry, M E in by delta T. So this W in means for the given period of delta T. Q in by delta T. Q in is for given period of delta T. Okay. E out by delta T. So we will take that part as there is a total mass out, that is M, okay, times E out by delta T. So total mass out, let's say M. No, it's M, okay. Okay, this one. So this is the expression there for delta T time. Okay, for delta T time, this is the expression. Equals 0. We can, if we rewrite this, so you can say M by delta T times E. Okay, M by delta T times E out. So M by delta T E in times means M dot E in. M dot E in. So W by delta T plus Q by delta T means W plus Q dot minus, here you have M dot E out. M dot E out. That is 0. Bigger fonts. This is same as the equation on the top. This one. Okay, equation on the top. So E is this. E is this. E means flow energy. Okay, flow energy. Or energy of a flow. Okay, energy in flow in or out. Potential energy, third term. Kinetic energy, second term. Internal plus flow work, H, okay, per kg per unit mass. Okay. Is this. So you substitute this here, you will get this. So is this. So you can substitute here. The big equation came out of this. You understand? Okay. For delta t period of time, energy 30 minutes. It's a work done. Heating energy as a rate. So this is, so you divide by delta t, you will get this. Then further rearrange this. So the mass in is in mass times E. This is the point. In is mass times E. In you can consider, because always per unit mass energy times the mass is energy total. So this is very nice. So E out. So you consider mass times E out. Instead of in, out is there. So you are substituting this in and out. Okay. So two equations. So make this little small. So equation 1 dividing by delta t. This is 1 by delta t. This is 1 by delta t. Then this is the two sets of equations.
සර් මේකේ C කියන්නේ තාපධාරිතාව නේද?
Now the velocity.
Okay.
Velocity, yeah, thank you. So two sets of equations are here. Two sets. So in is in times E. Okay. So further rearranging this way. Further rearranging this way. Finally this, back to this. So H can make equation. Let's say this is equation E. Just put equation E. Let's say this is equation 1. Equation 1. This is equation 2. Equation 2. Okay. Equation 2. This is equation 1. Equation. This is 3. This is 4. So back to equation 1 here. So back to equation 1. Back to equation 1. So equation 2 is
So equation ඔක්කොම open system වලට නේද?
open system. Very good. මේක තමයි E කියන එක. E is this. So I will put E somewhere here. Open systems. Okay. I will put E here. This is E is here. So when you substitute E in and out, you have this. Okay. So this is E. හරිද පුතා? තේරෙනවද මේක? Summary. Also you can rewrite this one. So take this out. This one you can rewrite H separators. H in minus H out. So separators. H in minus H out. Same way plus we have to have the other two terms. C squared in and out. Okay. Instead of this, C squared by 2 in. Velocity, C squared by 2 plus G Z in minus Z out. G Z in minus Z out. So this is the other form. Plus W plus Q equals C. Also possible. also possible. For some cases, okay, for some cases, let's say this is the steady flow. Now we will go for case by case, okay, case by case. Let's say turbine, okay. Let's say for turbine now. So if we look into open systems, turbines, compressors, then nozzles, diffusers, turbine, compressors, nozzles, diffusers, expansion valves, diffusers. So these are open systems. Even these are components. So we can have heat exchangers on boilers, whatever these things we can use. So let's say the very basic components here. Heat exchangers also we can have. Heat exchangers. So compressors, turbines. Okay. So if we go to a turbine here, so you are using this equation. So let's say turbine, Zn minus Z1 may be negligible. Maybe negligible. So then the equation can be simplified. So even compressors can be negligible. Nozzles can be negligible. Diffusers can be negligible. Expansion valves also can be negligible. This time, heat exchangers, because the difference is not much compared to others. So even expansion valves, some other can be W dot, can be 0 for expansion valve. Q dot can be 0. Okay. Heat exchangers, more work done. But of course, heat is not to say zero. Okay. Special cases, diffusers, no work done. Because work done, there should be something like a engine turbine, or the mechanism should produce some work. No sense, no work done. Compressors, W, yes. So compressors, W, yes. Heat, yes, unless you assume. Okay. Turbine, W, yes. Heat, yes. Okay. Nozzle, W, surely no. Heat, heat. So can be yes or can be no, depending on the assumptions. Diffusers, heat can be yes, no. If there are heat leaks, can be yes, no. Heat exchangers, heat, of course, yes. Heat is yes. That is right. So this is not necessary to be turbine for all the components. You can have this. So when it comes to analysis, the best is you take this equation and based on the equation, how many terms are there? 1, 2, 3, 4, 5. Okay. So you have m dot times h in minus. M dot times this. M dot times this equals 0. Equation number 2. So you can have a table 1, 2, 3, 4, 5 terms. 1, 2, 3, 4, 5, 6. Let's say 6 here. So let's say this one. So velocities, kinetic energy term, potential energy term. Okay. So this is the enthalpy term and your work done. W dot term, Q dot term. you can have this way. Then whatever analysis, it's a turbine example, W dot, yes, Q dot is 0, sorry, Q dot, yes, this is 0, others you have to evaluate, so these are the special cases, so turbine, compression,
So there should be a W dot.
yes, W dot, yeah, sorry about that. So you can have this kind of table, compressions, you can say mainly for the compression, many analysis, W dot, I will change the colors. Colors actually පැහැදිලි නෑ නේද? Okay, should work. So you have W, M dot in, M dot, H in minus H out. Compressions. Let's say if I assume 0, okay, assume 0, no heat loss. Assume 0, 0 means negligible. Assume 0. Then compression equation becomes what? So dot, this one, H in minus H out, this one, dot H in minus H out plus W is 0.
So in the compressor there should be a Q, no?
Yeah, there should be Q. Yeah. If I assume 0 example, right? So finally the equation becomes W dot. There should be 0. Yeah, I will put Q dot. Yeah. Because if not given, you can assume as 0. Not to say 0, but can be negligible. Right? So you have these three terms. Then your equation can be m dot H in minus H out plus W dot plus Q dot equals 0. Likewise, for these 5 terms, you can have these 5 columns. So turbine also, m dot H in minus H out, then this. You can assume 0 for the, hard to say, you cannot assume 0 in big ones. This one can be 0, assume 0. You have W dot and Q dot. That's all. So this one depends. depends. So nozzle, example capillary, let's say capillary. Capillary or the expansion device, let's say capillary or the expansion device. You have no work done. You can assume 0 here, assume 0. Let's say this is for example. If you assume 0, work done if you assume 0, if this is assumed 0, even if this is assumed 0, so you have only this one. So finally you have this. So your equation becomes this equals 0. So your H in is H out. So you have that kind of expressions. All depends. Capillary or expansion one. If you take expansion one, but assuming 0 for the velocity change, it's a question. Okay, that's fine. Assume 0. So for the capillary, we can see constant enthalpy. Generally, we consider enthalpy no change, but of course there is when you do the simulation, that's why if you do the finite element capillary piece by piece along the capillary, you are considering the velocities. That's why. So it's quite interesting. If you go to the textbook, yeah, let's see. If you go to your textbook, Nonflow process is easier one. So today I did only the flow process for that. Flow process. See boiler, condenser. So here for the thermal, okay, steady flow process systems. It's a solid example if you take this one. So for this case, in the textbooks, in your textbook, right? Yeah. In your textbook, let's say boiler, okay, boiler. So you consider kinetic energy terms, you neglect. Potential energy terms, neglect. Okay. W, work done, neglect. Then you have only Q. Okay, then you have only Q. Now, if you take the boiler here, boiler. So you have, see, again the same term, you know, M dot. See, boiler term M dot is here. So kinetic energy and the potential energies, we assume 0, and work done also assume 0. And you have only Q dots. They are using the same dots. So we are okay with your text. So it's happy to know that. Q dot is here. So Q dot plus this equals 0. So that is our expression, right? Q dot. So M dot H out minus H in. Plus Q dot becomes
Excuse
0.
me, sir.
Yeah, beta.
Yeah. So what is the meaning that 41, 21, that numbers?
Okay. This one is the cycle in the textbook. So where is that? Can you see this? This is for the this power plant cycle, yeah, this one. In a steam power plant, you have these components. Later we are going to discuss boilers, turbines, condensers, and feed pumps. So here 1, 2, 3, 4. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. That's how this came. 4, 1, and all. So now you can see Q dot 41. Q dot 41 is for the boiler. Turbine W dot 12. Okay. But here put 2, 1. Yeah, it should be 1, 2. So condenser Q out. Okay. Q dot 32 is mentioned. Q dot 43 for the feed pump. Okay. So this should be the cycle based on this in and out. So we'll go back to our case. So don't worry about the 4121, just focus on the Q dot, that's all. So based on this equals 0. So your expression Q dot is sorry.
So we cannot see the previous one.
Thank you. Thank you for reminding. So the same way for the boiler, this is the boiler. Okay, so you have the M dot term, H in and H out. Kinetics assume 0, potential energies assume 0, the differences, no work done in the boiler, so you have Q dot. So this equation, because this plus, this plus, this plus, W plus Q dot, all plus plus. Okay, so 5 terms reduced to only 2 terms. So your Q dot becomes M dot H in minus H out, that is minus. Okay, minus. So minus M dot H in minus H out means if you take minus out, so this is something like M dot H out minus H in. So this one we will discuss with some examples so you can see this for the boiler. Okay, capillaries, compressors. So turbine, where is turbine? Yeah, turbine here. Turbine see only the W term. Even here the velocity term assumes 0. for this case. Okay, for turbine. So W and M dot, H in and H out. So condensers, those are the heat exchangers. You can have the same way. This is the boiler. Condenser, so I will take instead of capillary, okay, let me put condenser here. Condenser. Always you have to consider the enthalpy term. So kinetic energy term, negligible, potential energy term, negligible, and even work done is negligible. You have only Q dot. That's why for the condenser you can see M dot times some enthalpy difference. So when it comes to feed pump is something like a water pump. Okay, feed pump. The water pump. The first example we take in open system. Water pump. The enthalpy is here. Kinetic energies, potential energies, heat transfer also consider assume zero, and you have only the work done for the pump. See, so the finally power M dot H in minus H out plus W dot is, so W dot is M dot times enthalpy difference. Enthalpy difference. So based on the assumptions only we can have this. You got some idea of it? Okay. So in your textbook, you analyze this two. Okay. One and two. Before that, let's see diffusers, turbines here. See gas turbine. So reduce to this equation. Turbine and compression. Nozzles reduce to this, and diffusers. Because Q dot, W dot, and also the gravitational potential, all the three terms gone. So nozzle and diffuser. Nozzle and diffuser. It's not here. So if I go to new slide. If we take nozzle, so velocity is important. Okay, so you have this. So no work. You can assume zero for heat for a simple cases. Otherwise you cannot. Gravitational potential you assume zero. So finally reduce to this. So this plus this is zero. Diffuser also the same. You have this term, you have velocity term, and all the others become 0. In your textbooks, in your textbook. Compressors and turbine, we have done here. You can see turbine and compression. Capillaries or throttle valves means the capillary, capillary or throttle valve or metering systems. It's the same. So you better look into the textbook, and then I will give you some assignment, notice assignment. Try to analyze this solved examples on page 27.
So what are the components affected by gravitational potential?
Gravitational potentials are generally for the piping systems. When it comes to piping, let's say in the plants and all, the pipings are going up and down, you can see at bigger elevations. So only in the pipes you can see. Other than that, actually the point is gravitational potential is negligible for this, the difference. Let's say piping systems, if we look into piping systems, can you see? So here in the modeling of piping, the gravitational potentials are considered sometimes for cooling there are taller heat exchangers, maybe boilers, condensers, evaporators in the processors. So there, when we see certain elevations and also the velocities are low. Velocities are low, which means if that is significant compared to the others, then we have to consider gravitational potential. The difference compared to the other 5 terms, if that is significant, let's say more than 1%, we may have to consider it. Let's say gravitational potential difference compared to the others. If it is more than 1% example, you may need to consider it for the accuracy. Example. Yeah. So mainly what we see in the pipings. So slow velocities sometimes, also running in elevations. For the accuracies, we have to take this, and especially to evaluate the pressure heads and all, we may need to consider this for the complicated pipings. Other than that, turbines, compressors, nozzles, diffusers, gravitational potential is negligible. So today, try to do this, okay? Page 27. Solved examples, even solutions are there. Huh? Yeah. We can discuss this. Not today. This is 12:22 now. Write down the general form for the steady flow energy equation, and it is reduced form for a turbine or a compression, a nozzle or a diffuser, boiler and a condenser, and a throttling process, stating any assumption made. So we just assume zero. You see, that is the assumptions. So question 1 is the same thing what we discussed. Then question number 2 about the gas turbine. Okay, gas turbine. The mass flow rate. See, m dot is given. Power W dot. See, 14,000 kilowatt. Enthalpy, see, per kg. That's why that is important. Actually, we can do this now. And the velocities are 60 and 50. See, 150. Heat is rejected. Yeah, we can do this. In a turbine, okay? So I will take the turbine expression also, because we have done for turbine. Turbine. So you have the table. Okay. If you need the expression, this is the expression. Right? Turbine. You have m dot 17 kilograms per second. Okay. So m dot 17. H in minus H out. Inlet and outlet are 1200 and 360 per kg. You have to watch the units. Because if it is not per kg, you cannot take m dot. So H in 1200, H out 360. The power developed by the turbine is 14,000 kilowatt. This is 14,000 kilowatt. The velocities inlet and outlet 60 and 150. So you have to take, see here, this is we have to consider. So m dot is 17. In is 60, because when the turbine inside working fluid expands, velocity will be more. 60 squared by 2 minus 150 squared by 2. And actually this in you can have here or even near the C in squared or whatever. Okay, 1 by 2. This is your expression. So Q, you asked to find what Q. Now, so the gravitational potential you can assume as 0. So the expression is 1200 minus 360 times 70. 1200 minus 360 plus the other term. See, plus the other term W dot 14,000. Make sure the units are matching. All kilojoules, kilowatts. So kilowatts, Q dot in kilojoules, but this one, that's why the velocity one in joules. So velocity terms, you have to divide it by 1000 to make it kilowatt. Otherwise, it's in watt. See, velocity term to go into kilowatts. This one. Now this is kilowatt. Kilowatt. In kilowatt. This is in kilowatt. That's why you have to make sure the units. This is in kilowatt. All in kilowatt. Assume 0 also in kilowatt. Okay. So Q dot in kilowatt. So this is equal 0. Single equation. Quite simple. Now you can get the answer. Okay. That's all. So here the velocities are considered for the kinetic energies. Potential energy, we have to assume generally it's difference. We would say difference. You cannot separately in and out potential energies, you cannot make it 0, but the difference you can consider 0. Okay. So assume 0 here, kilowatt is okay. Okay. That's how the expression. So solved example also you can see the value. පුතාලා තේරුණාද අද කරපු ටික? ටිකක් තේරුණා? This is one of the important piece of knowledge. ලොකු සමීකරණ කියලා මතක තියාගන්න අවශ්‍යයි. Try to get familiarized this. So you will have some answers here. Is that right? Any questions? Any issues? All understand well?
Okay, sir.
Okay, Ned. Then you look into this Putala page number 27. See, you have all, but here the kinetic energy is all separately calculated in and out. That is okay, but you see Q is a negative value, so heat rejection is there. Yeah. Heat rejection is there. You can study this also. This is the use for the per unit mass. That's also okay. See another one, steam interceptor turbine. Now this one we used to analyze this. Can you remember last week also? We tried to analyze this. This is the other one. So you can try this one also. Page number 28. Also try to do. Page number 28.
සර් ඔය ඩොකියුමන්ට් එක අපි ගාව නෑ අපිට අර වෙන එකක් ඒ විශ්සේ
ඒත් මේ ටික ඇති පුතා. නැද්ද? ඉතින් page number 28.
සර් අපිට හම්බ වෙන අර පේජ් 82ක් තියෙන එක
ඔව්. මේකේ 84යි තියෙන්නේ. මොකද බලන්න මේක තියෙනවද කියන්නේ.
ඕක හම්බුනේ නෑ සර්
නැද්ද? මේක තියෙනවා පුතා. ටියුටෝරියල් එකක් තියෙනවා. පොඩි වෙනසක් ඇති.
ඒ ඩොකියුමන්ට් එකේ 27 වෙනි පේජ් එකේ ඉඳලා තියෙන්නේ ඒව තමයි 27 32 වෙනකම්.
තියෙනවා නේද ඒ ටික? ඔව්.
ඔය දැන් කරපු ටික තියෙනවා සර් ඒකේ.
ඔව් තියෙනවනේ ඒක තමයි. So this one we have to okay. So now it's very simple. Once you drill the concept, you are okay. මේකට steam table එක use කරන්න හොඳයි නේද? This is the flow system. Non-flow is nothing. Non-flow is nothing because for non-flow system, no in, no out. Okay, of mass flow. No in and no out of mass flow for non-flow system.
සර් නන් ෆ්ලෝ එකේදී අපි කන්සිඩර් කරන්නේ W එකයි Q එකයි ඉන්ටර්නල් නේ සර්
එතකොට non-flow එකේදී ගත්තහම වෙන්නේ අර ඒකදී අපි non-flow ගත්තාම that is not steady පුතා. සේරානේ non-flow. Something like so this one. I will take a page. Non-flow. And let's say this one. Non-flow means this is for steady flow open. Once closed, it is no more steady flow. එතකොට flow කියන එක නෑ. Non-flow. So flow කියන එක නෑ. Okay. So this become closed. Okay. Closed. So steady flow, in and out, all. Mass balance. No. Okay. So mass flow in, energy in. No. Okay. Mass flow out. No. Okay, but system is only work and heat. Whatever mass remains. That's all. Huh? So it is something like so take this side. No in. mu out. Okay. Maybe case if you put mass flow, mass balance, no relevance. Okay. So no M in, no M out. Okay. So that's how it is. So no M in and no M out. No M in, no M out. That's a mass flow condition. So work and energy balance. So no M in means E in, E out. No. Okay. All gone. Okay. Then you have Q and W. E system years, time delta T years. So E in, no. E out, no. Okay. So this is very nice. So finally, this simplified to W in plus Q in. So that is the net. W in plus Q in is delta E system. So standard is, since all we take in W plus Q, whatever W, all net. Q this. Delta E system now changed to delta U system. So delta U system. So since it's for the system all, even you can take the word system out. Okay. So W plus Q is delta. Okay, so that is the equation. So if your system mass is M, okay, if your system mass is M, then you can divide this by M.
So you mean internal energy, no?
Yes, of course, internal energy. Because no pressure, no flow work, no H by M. M is the mass of the system. Even you can use big M. That is also okay. So this is W by M, Q by M. So W by M plus Q by M. This is small w plus small q. Small w plus small q is delta small. So here the unit is kilojoule per kilogram. Here unit is kilojoule. Here unit is kilojoule per kilogram. Quite interesting. This is quite easy. So that's all. So any closed system, so all live and steady, of course, live and no steady, live. I think I will take this out. Okay. You have the surrounding, yes. Boundary, yes. Only heat and work. So no more turbine here. Okay. No more turbine. Not heat. So if I make this more organized, no in, I take this in out. Okay. Move out. So we can take this out. Because no need to mention what is not there. As it's not there. W here. QVC. M system. E system. So we use the big M. So I will take small m. So whatever I'm saying, I will take it down. Work and energy mode. So this is not to say steady, this is non-flow. Okay, non-flow or flow system. I'll take this out. No M in, no M out. Work and energy balance. So E in, E out is no more there. Q in, W in, E system. Okay. Time T delta T is okay. Delta T. In. E out. Delta E system. Delta E system means delta U system. Okay. Quite nice. Okay. Nice. So if you need an example, you can do that. See, non-flow processes item 2. Q plus W is U2 minus delta U. Before process is 1, after process is U. Here. Chapter 2 is non-flow process. So it's Q plus W. U2, this is delta U. Okay. Before process 1, after process Of course, there are constant volume processes, and there are we have to study this. But this is no big deal, right? Non-flow processes. We have to do this a bit. Chapter 3, flow process, steady flow. We have done this very well, steady flow process. Chapter 3, so we are moving forward. See, m dot in, m dot out, m dot in, everything same, looks the same. Okay. Control volume. The system is okay, but this is the volume. So we can mention as control volume. Conservation of energy, steady flow. So all are the same. You have to go through this by yourself. Right? That is very important. Chapter 1 is about the steam and all. We have touched a bit. Here I need to give you one example. Solved example, page 18. You can look into this in your text. The process. Good. So piece of knowledge is here. This is the question. Now you can look into this. This question I just put in the PowerPoint also. Try to study this. Doing a question means you are really analyzing this. Good. So this is the one. I'm showing you the process. Even steam tables also are here. This one we're supposed to do it. What is the question I asked you to do? Non-flow process tutorial was here. This is the question if I'm not mistaken. Page number 18. Okay, page number 18. There's a question. Try to do this. Okay. Quite easy one. So, quite easy one. Try to do this. So that's all Putala for today. So we have done something sizable. But yesterday it was really good. So today we have touched the steady flow processes and also non-flow processes. We have learned from steady flow, not a separate one. So page number 18 tutorial try to do. So try to understand this and just go through the note. Okay, go through the note. And we supposed to do these tutorials here in the notes. So slowly we will do it, don't worry. So that's all for today. Any questions, Pitala, before winding up? Any questions? Any questions? Okay. Then see you next.
So next week, time as usual.
Yeah, Puta. Saturday. Saturday.
Okay.
Yeah, Saturday normal time.
Okay.
Saturday normal time, 1:30. Generally it's 2 hours, but today somehow this prolonged for 3 hours plus. That is okay. As long as you are there.
Alright, sir.
So go through the notes, Putala. So my lectures are only a helping hand for the notes, and you are receiving something out of the notes during these discussions. So that helps you. So trust me, if you do this first 6 chapters, or if you have a full understanding, you can have a very good marks. And don't worry, I will don't give things outside this text.
Excuse me, sir.
Oh, yeah, Buddha.
Sir, can you send the today notes?
Can.
Yes.
Yeah, let me email it to you now. Let me email it to you now. So the notes are, we have to do some bit housekeeping on the notes. But anyway, I will send this as it is. Remember, this computer programming, this is the time for you to pick up the subject, because after graduation it's very difficult to pick up it. So if you have the interest now, better do, even though the lectures are not conducted at these days, in these days, do some self-studies and try to pick up this programming. That is extremely important. තමයි notes වල proofread කියලා නම් නේ අපි මේ වෙලාවේ type කරපුවම ගොඩක් තියෙන්නේ. So if there are some issues, just let me know. Right? Yeah. Acknowledge? Yeah. So we will receive it now. බලන්න හම්බ වෙනවද කියලා. හම්බ වුණාද note? Did you receive the note? හරිද පුතා? Okay. Good. And today attendance also only 14, same like yesterday.
Yes, sir, we got the note.
Avita? Oh.
We got the notes.
Okay, okay, good. So please encourage your batchmates to join the lessons. That would be pretty much helpful, really.
Okay, sir, we'll do that.
Okay, okay. So let me stop the class now. Bye. Bye.
Okay. Thank you.
Care, okay, bye. Bye.
Thank you, sir.